Section 3 on geometric sequences and series. A sequence in which the ratio between successive terms is a constant is called a geometric sequence. The constant is called the common ratio R. So if you notice in a sequence that it's being multiplied by the same number to get to the next term, that's a geometric sequence. And whatever number is being multiplied is the common ratio. The equation to find the nth term of a geometric sequence is a sub n equals a1 times r to the n minus 1 power. So you can use this formula to find any specific term within a sequence, or if you have a first term and some subsequent term later on in the sequence, you could find or solve for the common ratio as well. So example 1 says to find the common ratio and the next 3 terms in the sequence after the last one. So we go from 8 to -2 to 1/2. So to find that common ratio, you can always take a term and divide it by the preceding term to find the common ratio. So if I do -2 divided by 8, this would give me my common ratio R. I could have also done 1/2 divided by -2, and you would get the same thing. So the common ratio for this sequence is -1/4. So now I'm going to continue the pattern to find the next 3 terms in the sequence. So 1/2 times -1/4 will be -1/8. -1/8 times -1/4 will be 1/32. And 1/32 times -1/4 will be -1/128. Example 2 says to find the explicit formula and the recursive formula for this sequence. So before we find both formulas, we need to find the common ratio R. So just like in the last example, you can take any term and divide it by the preceding term, and that will give you your common ratio. So our common ratio this time is 25 divided by 2, which is equal to 12.5. So we're going to start with the explicit formula first. So the formula was a sub n equals a1 times r to the n minus 1 power. So we're going to plug in the information that we know. A sub n equals 2 is our first term in the sequence. And I go ahead and write the common ratio in parentheses so it doesn't get too busy with multiplication signs and looks a little crazy. Our common ratio we said is 12.5 and then raised to the n minus 1 power. So if I want to find the 15th term in the sequence, I can plug in 15 for n, and that would give me the value of that term. The recursive formula, you have to know the first term in the sequence, and you have to know the preceding term to find the next one. And that's kind of what we were doing. Once you found the common ratio, you multiplied that times a term to find the next term to continue the pattern. So our first term is 2, so a1 equals 2. And then you're always going to write a sub n equals a sub n minus 1 times 12.5. What that means is any term in the sequence is going to equal the term before that times 12.5. Example 3 says to find the common ratio in the term named. So we're going to find out what R is, and then we're supposed to find the 27th term in the sequence. So for my common ratio, I'm going to divide 151.2 by 189. And that reduces to 4/5. So I'm going to use the explicit formula. A sub n equals a1 times r to the n minus 1 power. So since we're trying to find the 27th term, we have to plug in the first term, the common ratio, and 27 for n. So a sub 27, that means the 27th term is going to equal 189 times 4/5 raised to the 27 minus 1 power. So you can type that all into your calculator at one time if you want to, or you could do it separately, find out what 4/5 is raised to the 26th power, then multiply that times 189. So this is approximately 0.57, and I'm rounding here because this type of sequence, when you multiply by 4/5 each time, the decimal is going to go further and further out. So it's okay to round in this case. So if two non-consecutive terms of a geometric sequence are known, the terms between them can be calculated. These terms are called geometric means. And we had problems like this with arithmetic means as well, where you have a couple of terms, but you're missing ones in the middle. You have to find out what those are. So in example 4, we're given the first term is 480 and the fourth term is negative 7.5. We're trying to find out what these two missing terms are. So we're going to use the formula for the nth term of a geometric sequence. We're going to plug in negative 7.5 for the nth term. 480 is the first term. We're trying to solve for r, the common ratio. And since negative 7.5 was the fourth term in the sequence, that's why the exponent is 4 minus 1. So I'm going to rewrite this, and we're going to divide by 480 on both sides first. So negative 7.5 divided by 480 is negative 1 over 64 equals r, and I went ahead and subtracted. 4 minus 1 was 3. So since we're trying to get r by itself and it's being raised to the third power, I need to take the cube root of both sides. So the cubed root of negative 1 over 64 is going to be negative 1/4. So negative 1/4 is our common ratio. So then I can use the common ratio to multiply by 480 and fill in those next two terms in the sequence. So negative 480 times negative 1/4 is negative 120. Negative 120 times negative 1/4 is 30. And then to make sure, I could do the same, 30 times negative 1/4, and that would equal negative 7.5. A geometric series is the indicated sum of the terms of a geometric sequence. So the sum of a finite geometric series. So this means if I have a set list of a geometric sequence and I want to find out the sum of those, then I can use either of these two formulas. And it just depends which information you're given as to which one you want to use, whatever your preference is. And then last, down at the bottom, is the sum of an infinite geometric series. So this is a list of a sequence that would continue on forever. If I want to find the sum of that, I can use this formula. Okay, so example 5, we're going to evaluate this geometric series. So that means if I was to list out the first 6 terms of this sequence and then add them together, that's what the sum is going to be. We can use one of two formulas. We're going to use this one, S sub n equals A1 times 1 minus r to the n power over 1 minus r. So we're going to find our common ratio by doing 14 divided by 8, which reduces to 7 over 4. Then we can plug in our values. So S sub 6, since we're doing the first 6 terms, equals A1, which is 8. In parentheses on the top, I have 1 minus 7/4 raised to the 6th power, since it's 6 terms, over 1 minus 7/4 again. So I would be very careful if you type this all in at one time, or if you want to take it piece at a time, you can. If you type it in at one time, I would put parentheses around the top and bottom of this fraction. That would make it a little easier, and it will make sure that it comes out correct. So when you find the sum of these first 6 numbers, it is approximately 295.71. So the purpose of this formula is if in reality I had a sequence and I wanted to find the sum of the first 500 terms, I don't want to list out all of those 500 terms and then add them together. You can use the formula instead, as long as you know the first term, the common ratio, and how many terms you want to add up. Okay, so example 6, this is the same thing. This is just written in sigma notation, and we saw sigma notation in an arithmetic series as well. So this is saying the sum of 3 times 5 to the n minus 1 power from the second term to the 7th term in the sequence. So some of you have already figured out how to type these in your calculator, which is fine. Those of you who haven't seen it yet, I'm going to show you the steps. So in your calculator, if you hit the math button and you go down to 0, you're going to see summation, and it should have a sigma symbol with an open parenthesis. After you hit enter in your calculator, it's going to have little boxes for you to type things in. And you're going to put X and a 2 at the bottom and then a 7 at the top. And then you type your equation just like it is in the problem. We could plug in 2, 3, 4, 5, all the way to 7 and find out what the sum of this series is, but your calculator has this summation notation for you. As long as you plug everything in correctly, you'll get it right. So the sum of this series is 58,590. Okay, and the last example, number 7, says to evaluate the geometric series. This is an infinite series since it has 9, 3, 1, ... It's going to keep continuing. So first we need our common ratio, and then we're going to plug into the sum of an infinite series formula, which is S equals A1 over 1 minus R. So our common ratio is going to be 3 divided by 9, which is 1/3. And you can see that they're multiplying times 1/3 each time to get the next number in the sequence. So in our sum formula, we're going to do 9, since that's the first term, divided by 1 minus 1/3, which is our common ratio. And again, I would put the denominator in parentheses if you type this all in at one time. So the sum of this series would be 13.5. So it seems odd that an infinite series, something that's going to go on forever, that you could actually add up those numbers and it's a tangible number, not just infinity. So it works out that if you kept multiplying by 1/3 and you add up all those numbers, it's going to equal 13.5.